Dear colleagues, good afternoon. My name is Maxim Baranov. Uh, Today I will present my presentation named by Investigation Methods of Dehydrated Protein Films for Biomolecular Electronics. As modern semiconductor microelectronic reaches its physical limits, new principles, materials, elements and devices are required to tackle this problem. Molecular and particular biomolecular concepts can be incorporated into the design of new electronic devices. Developing molecular electronics is an urgent task which can be solved by drawing on the unique electrical properties of organic components and their hybrids with solid-state electronics. Practical implementations of biomolecular electronic devices, especially for development telecommunication technologies, necessitate further studies into physical phenomena in biomolecular structures and clusters, for instance transitions and self-assembly processes in thin micromolecular films, and several related physical phenomena. To construct these devices, it is imperative to understand the mechanism of intra- and intramolecular interactions, charge transfer processes, dynamics of thin liquid films, the influence of external conditions on the biomolecular structure's properties. Stable self-assembled macromolecular films on substrates are the focus of considerable scientific and practical interest for creating the elements of new electronics. Such films show promise as functional materials. Therefore, thin protein films can be used in optics, biosensors, electronics, drug delivery, antimicrobial coatings, and food packaging. Self-organized biomolecular films are ordered molecular structures. They are created by drying an initial liquid solution of biomolecules on a solid support. It has already been shown earlier that it is possible to obtain various structure types, which depends on the amount of salts in the initial protein solution. Typically, structures are classified into two types, cracks and dendrites. Cracks are mainly formed from water solutions or the original proteins, and they are linear, radial, and spiral. The dendrites are usually formed as salt crystals found in the initial protein solutions and can be in various sizes and shapes. The aim of this work is to study the processes by which stable biomolecular films can be obtained from solutions with nonlinear impedance necessary for creating novel biomolecular electronics. We used the methods of optical microscopy and computer simulation to consider self-assembled biomolecular films obtained under different conditions for dehydration of aqueous solutions. On the slide, a schematic representation of an experimental setup of optical microscopy method is presented. The molecular dynamics method was used to study the free energy. Molecular system models were modeled using Visual Molecular Dynamics program. Each of them was a system of two albumin protein molecules. The minimum distance between individual regions of these molecules was about 3 angstroms. The studies were carried out in the cubic water volume with the addition of sodium and chlorine ions. The studies were carried out at NPT configuration, constant value of number of particles, pressure and temperature. All simulations were carried out with a CHARM27 force field using the nanoscale molecular dynamic package under periodic boundary conditions and a cutoff radius for unrelated interactions with a switching function starting from 12 angstroms and reaching 0 at 14 angstroms. For these experiments, albumin protein solutions were prepared with a concentration of 5%, since this is the optimal concentration to obtain standard spiral structures. Then the usual drying of experimental samples were carried out at various dehydration temperature. The results of these studies are presented in this slide. It can be seen from images. The number of spiral structures decreases with increasing temperature, although the films become less stable and the nuclei of future spirals begin to form without the formation of spiral cracks. A graph was plotted as the number of spiral structures versus temperature. These dependencies are shown in this slide. Studies of the processes of self-organization were carried out using the method of molecular simulation. Calculations were carried out at the same temperatures. Graph of the dependence of the energy of molecular clusters from time are presented in this slide. Analyzing this graph, it can be noted that with an increase in modeling temperature, the total energy of molecular clusters increases. As we can see in all experiments, this value has a negative sign. Relying on the results of previous studies, it can be said that with such an energy sign, the precluded film has a positive adhesion to the surface. Comparing the results in all figures, it could be noted that with an increase in the dehydration temperature, the number of helical structures in the films decreases, and the energy of biomolecular clusters increases, tending to the positive range of values. Current research is aimed at studying the properties of thin films. Since in the future these films may become a material for creating elements of devices for biomolecular electronics. The properties and stability of these films under the influence of direct electric fields of various magnitudes are currently being studied. An aqueous solution of albumin protein was used with different values of the volumetric concentration of protein in the solution, 5% and 2%. External electric field was applied to the samples with 0.25, 0.5, 1, 1.5, 2, 3, 4 and 5 volt by centimeter intensity. The area of the film surface was the same for all experiments and was equal to 0.1 cubic centimeter. Various images were obtained containing quasi-periodic structures, consists of certain cells about 200 nanometer in size each. On this slide we can see albumin protein solutions films with 2% of protein in initial solution. On this slide we can see albumin protein solutions films with 5% of proteins in initial solutions formed under the influence of an external electric field. This slide shows a graph of the dependence of the number of spiral structures on the value of the applied electric field. The structures were counted on the entire surface of the films. Analyzing this dependence, it can be concluded that the electric field affects the cracking of protein films. The molecular dynamic methods showed that with small changes of the external electrical field, the order of the volt by centimeter units, the total energy of the molecular cluster remains almost unchanged. This is presented on this slide. On this slide we can see that the energies of molecular clusters are increased by 2/10 of a power in comparison with previous slide. For 5 nanoseconds, the energy indicators do not have time to reach the stationary level, because the processes of destruction of the protein structure is in progress. So, comparing the results obtained by optical microscopy method and modeling molecular dynamics, it can be concluded that big constant electric fields do have effect on the formation of thin biomolecular films, but the full energy of molecular clusters are stable. This requires additional research. The main conclusions of this work are presented in this slide. Thank you for your attention. Goodbye.